All right, should be recording. Okay, so tomorrow at 5 o'clock, Dr. Teague is coming, and he's outside the door is a little thing about what he's talking about. He actually runs the research at the O School of Community Medicine in Tulsa, and he is a former Southeastern student. I did not have him in class. There are a couple of those. Hard to believe, I know. But like I didn't have Dr. Smith either. They graduated in 90, and I started in August of. Dr. Smith said he remembers my interview talk because they fly around and give a little talk and all this. I had to leave my little baby at home with my husband all by herself. And so when you go, there's going to be a pad of paper. It'll say organic 2. Make sure you sign. Okay, and I'll be there. I'll be looking for you. But a week from then, I won't remember if you were really there or not. So, okay, all right. Is that good? 10 clicker points. His talks about immunology. So a lot of you will probably be interested in that. All right, here we go. Okay. Which drawing below is the MO that is lowest in energy for 135 hexatron? I'm thinking this little deal over here is going to go away. Oh, there, that's at least better. Hopefully it'll Uchi up. I don't know how to make it. Apparently I can make it come down real well. Can you see them good enough? They look blurry. So, I can't win with this group. You can tell the blues and the greens, right?
Yeah.
Okay. Sorry about that. I'll make sure they're print clear on the test. So. Even if I have to redraw them all, I will. Okay, I got 18. Is that everybody? Did you pick a list?
I mean, I did, but I don't really know what's going on. So.
Oh.
I don't know. I don't know how you tell about homo, but that's not what this is.
Well, you have to read the question.
Yeah, I guess. Yeah, I guessed.
Okay.
That's answer.
Okay, what is the question asking you? Which drawing below is lowest in energy? Okay, so what does that mean? It's the most what? Stable. The most what? Bonding. Which one is that? Because they're all the same. So these are bonding interactions between all of the lobes. Between everyone. Okay? There's one up there that is the highest in energy. Which one is that one? Which one's highest in energy? Hey, I should have put that on another question, shouldn't I? Okay, this is highest. Okay, why? How do you know that one's highest? The ones in the middle are the trickier ones. Because it's all nodes. I knew you know that. All right, this is what we were doing. And I told you to work on the bottom one. How's that going? Did you come up with an answer? Did you come up with an answer? Is that what you got? This is the one that you get. You don't get that one. Remember that you put the most negative and the most positive carbons together. So if you're going to draw resonance for this one, let's see if I can do it here. Bring in the butt head. Okay, so you can draw a resonance form for this. We're going to go there, and then where are we going to go? Then we're going to go all the way out to this carbon. Which carbon has the most electron density? It's going to be this one. Okay, this one right. That's the one with the most electron density. That's going to be the negative part. This is going to be positive on the O. Okay, now you look at the dienophile. I'm going to draw it all out so we have bonds. Okay, so how am I going to do the resonance for that? Yeah, I'm going to go down and out to the end. So which spot will be the least electron density? The lowest in that. It's going to be this carbon here, so you got to flip it. Put it together. So it'll be. That's how you decide which spot goes where. Okay, because you can put it together two ways. Okay, so it's going to be this way. How'd you like that? They were only all just. Okay. All right. Well, hang in there. We're going to hopefully finish this today. Okay. Here is an example of a diene and a dienophile. Okay. And I want you to notice that this tends to look real flat, this first picture. And so organic chemists like to draw things up. Okay. And here you'll notice that the cyano groups are pointing down. That is on the side of the molecule where these two carbons are. Okay. Here, they're pointing out. Okay. Notice that they're cis to each other in both of those. Three. Okay. And here, you could make them up or down, I guess, if you wanted to do that. Here, though, they're up by a 1 carbon bridge. This one is by a 2 carbon. Well, it turns out that this is the one that's formed, which is part of how molecular orbital theory got born, because they went trying to figure out why would you do that and not make the one that's least sterically hindered, because they're just going to line up. It's all in one. Okay. So this one is called the endo isomer, and this one is called the exoisomer. It's just, I'm not going to use those terms. I'm not even going to put them on the test, okay? But you might someday, I want you to know, oh yeah, I heard that, okay? It's very rare that I tell you something won't be on the test. Is it not? Okay, so here is a simple example, okay? And when the group is swung this way, okay, you get overlap where they line up, okay? If the group is out this way, you would get the exoisomer, okay? But that group, this is a different example, but this group here is going to help things out by helping to stabilize that intermediate, because those lobes overlap. Okay, that's basically why. All right, and that's how come we get the endoisomer instead of the exoisomer. Okay, that kind of makes sense? Remember that these are matching. This is where you're going to make the red and the orange are where you're making your sigma bonds, your new ones, and then you're going to end up making a double bond up here. Same thing over here, okay? But you have this orbital from this carbon, okay, is helping to stabilize everything. And that's how come it likes to do that, okay? Pretty simple. Okay, now we need to talk a little bit more about the dienes. by themselves, if you add bromine or chlorine, and if you add water with acid. Okay, so we did dienes plus HX, right? What do you remember about it? It was a whole day ago. Well, maybe. Did we do it before spring break? Might have been. So hopefully you have slept since then. But do you remember anything about it? Do you remember how many products you get? 2, okay, and what are they called? Remember direct and conjugate? Or 1, 2, and 1, 4? Okay, all right. We're going to do the same thing with this, okay? Maybe. Okay, so if you add bromine or chlorine, you can add 1 equivalent or 2 equivalents. Typically, it will say something in parentheses around the, after it lists BR. So I'll show you. So let's do the simplest. Let's add bromine, because we like bromine. And I'm going to write 1 EQ. Okay? That means 1 equivalent. So if you had half a mole of this, you would use half a mole of that. Okay? We're only going to add 1 equivalent. Okay? So if we add 1, 2, what does that look like? Our molecule is nice and symmetrical. So carbons 1 and 2 get the bromine. Okay, so that's the 1, 2 product. Or direct. I'll move out of the way. I realize I'm in the way. Okay, let me try using my pen. Okay, so what's the other one? Here is your clue. Okay. And then over here, right, we're putting the other, and in the middle is where the double bond is. Okay, why does it do that? You remember? Because you get that carbocation and it will rearrange a little. All right, so this is going to be the 1, 4 product or conjugate addition. I guess I should write the whole word. Okay. What do you think would happen if you added 2 equivalents or more? Sometimes it'll say excess, not extra small, excess. Okay. What do you think you would get if you did that? Yeah, exactly. Everyone. So in every spot, you get a bromine. So you get a whole lot of bromine going on. Okay? Do you remember which one of these is the kinetic product and which one's the thermodynamic product? Kinetic is formed faster. Thermodynamic is more stable. Okay, so which is which? What do you think of these 2? This one's only 1, so it's all of them. Okay, so what is this? Every reaction has a kinetic product and thermodynamic. We only talk about it here because it makes a difference, because they're different. Okay, so which one do you think is kinetic? The first one. So who's thermodynamic then? Why is this one more stable? The double bond is disubstituted, yeah. Okay, does that help you all remember? That's MIC right there. All right, so look at this first one up here and tell me what you're going to get. It's bromine, 1 equivalent. So what are we going to get? Look out of the way. Look at that, I have them drawn nice for you, obviously. That's why there's white. How many products do you think you get? 2. Very good. There's 2 white boxes. Unless I'm hiding some. And there's a plus between them, so we're going for 2. All right, so what do you think? 1 double bond is, notice the molecule's symmetrical, so we don't have to deal with that issue. Okay, but 1 double bond is going to get the 2 bromines. Okay, that's probably this one. Okay, no, it's not. Only I would not do it in the normal way. Okay, this one, notice the double bond moved. Okay, so this is your 1,4 addition, and this is your 1,2 addition. Okay.
Well, that's hard.
Yeah, I'm gonna fix it. We just need us some nice purple. There. Okay. What happens when you have 2 equivalents of chlorine? Every spot, right? We like those. You do have to be careful sometimes. The 1,2 and the 1,4 can be the same thing. I don't know that, let me see. The main place to look for it is rings. So let's do a ring one. Okay, and we'll do chlorine 1 equivalent, just so that you practice. All right, so here's your clue. I guess these wouldn't be the same.
So the 1, 2 be the first and the bottom, right?
So you're going to add chlorines. Okay, that's the 1, 2. Okay, and then what would be the 1, 4? Okay, so I'm going to put a chlorine here. 1, 2, 3, 4. And the double bond has moved to the bottom. Okay, so this is the 1, 2. This is the 1, 4. This is direct. This is conjugate. So that time we didn't get the same thing. Sometimes there's, if you add HCl, you might be the same. Okay? Got him? It's kind of easy. All right, what if you add water and sulfuric acid? So what happens if you have a plain, ordinary double bond, just one, and you add water and H2SO4? What do you get? Yeah, right. Well, 1 carbon gets a hydrogen, and what does the other one get? OH, right? We're just adding to the double bond. Okay, so that's basically what we're going to do here. Same thing, you protonate, water adds, deprotonate. Okay, so what we're going to do is add to this, but we're going to get 1, 2, and 1, 4. Okay, so can you draw those? I don't know if I can. I'm going to push a button. Okay, so which is, what do you think? Which is which?
First.
Here's what I'm going to do. I'm going to try to use the highlight. Okay, so here is your 4 carbons. So where did it add to carbons 1 and 2? The top one or the bottom one? The bottom one. Okay, here are those 4 carbons. Okay, does that help? Help you see it? All right, so this one is the 1, 2. This one is the 1, 4. Okay? The bottom one is direct, the top one is not. Okay? We don't use HCl or HBr. Why? Why do we use sulfuric acid and phosphoric instead of HCl or HBr? Because what will chloride and bromide do? They would add. So you would have mixtures, and then you'd have to clean it all up and it would be a mess. Okay? It's not fun. Okay, so UV-Vis is, here are wavelengths used in spectroscopy. That's what this whole thing is. Okay, so here we have IR. IR is 2.5 to 25 micrometers, or 2.5 to 25 times 10 to the minus 4 centimeters. All right, that gives you an idea how big that is. Okay, visible is 400 to 800 nanometers. We're getting smaller, right? Okay, that's visible. UV is 200 to 400 nanometers. Okay, so we keep getting smaller. Notice the visible region is really tiny. Okay, that's what we can see, what our eyes detect colors in. Okay, is only the visible region, except for Geordie on Star. Okay, or I'm sure some of those Captain Marvel see other. Isn't there a guy? Oh, the Cyclops guy. Does he see other deals, or does he just shoot rays on it? Okay, NMR uses radio waves. We won't worry about that. Okay, so the light energy is absorbed by an electron and it jumps to a higher energy level. The energy of the photon must be the exact correct amount. So when you're going to jump electrons, you have to give it the right thing. That's what that whole Planck thing is. E equals h nu. Okay, h is Planck's constant. He figured out what that number was. I don't know what Planck's constant is anymore. I forgot them. You can always look it up. All right, so there are 3 possible transitions: pi to pi star, sigma to sigma star, and n to n star. Okay, are we good on what a pi electron is? What do you think a sigma electron is? What do you think that is? It's in what kind of bonds? Sigma bonds. What is n, you guys? Non-bond. Okay. See how molecular orbital theory can all of a sudden get super complicated? That's why we only did what we did. Okay. Non-bonding. Give me an example of a non-bonding electron. Like what? A lone pair. Okay, lone pairs. Okay. Okay. Just so you know what it is. All right. So here is ethylene. If you give it the correct amount of energy, and I think I have what it is, you have to give it 171 nanometers. Has to be the wavelength of light that hits it. Okay. An electron will jump from the HOMO to the LUMO. Okay. We jumped up there. That's UV-Vis. That's basically all you're doing. You're jumping an electron. The more conjugated your system is, the easier it gets to jump an electron. Did you do a lab with chromatography with tomato paste? Okay. Sometimes we do that in organic. What makes tomato paste red? Does anybody know? A compound called lycopene, which is super big, okay, and full of conjugation. Double, single, over and over and over, okay? And that is really good for your body because notice what we're doing. We're adding UV radiation, and what is that electron doing? It's jumping, okay? If you eat tomato paste, you eat things that tomatoes, I guess. But if you eat tomatoes and things that have that conjugation in them, carrots is another one. What will happen is those molecules in your body will absorb that UV radiation that you get from the sun and help protect you. from UV radiation. That's why those things are good for you. That's why they tell you to eat them. If it's in your blood system and there's a free radical or something in there, it will scavenge those up, grab them, okay? Because it can easily pop an electron out. Okay, now there's some more pictures, aren't there? Okay, so here is 1,3-butadiene. Notice that ethylene was 171. 1,3-butadiene is 217. We got longer in wavelength. Okay, lower in energy. Longer wavelength, lower in energy. Okay, should pop that guy from the HOMO up to the LUMO. Okay, and the last one I've got is 1,3,5-hexatriene, and it's 258. So as we add a double bond, we're getting longer and longer. Okay. Okay, so UV-Vis. Okay, in the visible region, increasing conjugation causes absorption at a longer wavelength. So look at, we got up to 7 carbons, we're at 400 nanometers. Longer wavelength, lower. Okay. Okay, what we use UV-Vis for, first of all, if you have a molecule that is highly conjugated, you can put it in a UV-Vis and run a spectrum. Okay, I think I have a picture of one. Here's it. I'll go back to that other one. Here's a picture. Okay, look, it's not very exciting. Okay, but you can measure what the maximum wavelength absorption is for that molecule, and it will kind of be standard for that molecule. So if you're trying to decide if you isolated lysine for tomato paste, you can stick it in a UV-Vis and look at it and see what you're playing to max. That's the maximum absorption. It's going to be that specific wavelength for that molecule. Now, can you stick something in a UV-Vis and figure out the structure? Not really. Okay, you need NMR and stuff like that to figure out those structures. Okay, where you don't get a structure from UV. But what we do is we monitor reactions using UV. So let's say you're studying lycopene and you wanted to study how it does its thing in the body. What you could do is run something in a little cuvette. Okay, you know what a cuvette is? The little square things that you put in the UV-Vis that you're not supposed to touch you're only supposed to touch the 2 sides, right? That are not shiny or clear. Okay. So what is that? Okay. Okay. All right. So you would run a reaction in there and you would watch the absorption go down at that wavelength. Okay. So that's one of the ways that we use UV. Did you do something with a spectrum? That's basically UV. It's just one specific wavelength, I think, that those have. But there are a lot of UV-Vises that will run like a bunch of wavelengths at once and stuff like that. But you watch this go down and you can figure out kinetics and stuff. Okay? Don't worry, we're not going to do it. All right, now, you do need to know what Beer's law is. Beer's law relates the absorption to the concentration. So if you have when you use the Spec 20 in general chemistry, did you have some standards that you put in at first, and then you put your thing in, and then you figured out what the concentration was in your little cuvette? Does that ring a bell? Okay, because you do that using this Beer's law. Okay, the Beer's law relates absorption to concentration. Okay, and that is pretty nifty that you can do that. You can figure stuff out using that. Okay, I is the intensity of the reference compared to the sample. Okay, C is the concentration in molarity. Do you see this little ECl? Okay, E is the molar absorptivity of the sample. So you have, that's like a constant that you'd have to get. You would figure out your path length. That probably is pretty well figured out. Okay, and then you can figure out your concentration is unknown. So A is going to be the number you would get off the instrument. Okay, we're not going to calculate anything. But I don't want you to take analytical next year and have doctors say, what do you mean she talked about UV-Vis and say there's one, because he'll make it. Okay. I don't want you getting me in trouble. Okay, so here is some pumpkins and squash that have a lot of beta carotene. Here's beta carotene. Look at that picture. Look at that conjugation. It's huge, okay? There's a huge amount of it, all right? And lycopene has even more. More conjugation, look at that. Your wavelength is getting lower and lower. So you get to see different colors. Okay, now there's other things that make things colored too, but conjugation is the main thing in organic molecules. There we go. Okay. This is a picture of Saturn's rings taken using UV imaging spectroscopy. In case you wonder how they figured this out. It's not like we fly over there and get samples, okay, and bring them back home and figure out what they are. Okay, that ain't happening. Although the little Mars guy is running around on Mars getting samples, but he actually does all the analysis and just sends us the. So it's not like he's going to send us back, because then we might all die because he'd bring a little Mars. That's right. So it's a good thing. There's even places on Mars now that he's not going to go because they're worried there might be life there, and they are concerned. So the little rover, they're not going to let it go over there in case something from Earth would contaminate Mars, cause all the Martians to die. They're little one-cell creatures. No, they haven't found any. They've only found ingredients for life. They haven't found life yet. Yeah. All right. So this is Saturn rings, and they took it using UV imaging spectroscopy. Okay. The turquoise is ice, and the rocks and dust are the orange.
How do they know it's like? They don't.
Well, I think it's like what could live in a vacuum. I mean, since space is vacuum, I guess. You have to ask Mr. Sun. Y'all ask him. All right, that's it. That's chapter 15. Guess what we're going to do? We're going to do a question. And then we're going to start chapter 16. You really want to do 16. It'll be good to have it on the test. A little nomenclature. Okay, rank the following compounds in order of increasing lambda max in the UV-Vis spectrum. There's only 3 of them. How are we doing? I'm up to 15, 16. Let's warm up here. Did you print out the next chapter? It wouldn't be hard to write anything down. What we're going to do, you'll see. Okay, you can do it without having to print it out.
It's a big.
Ooh. Boy, I hope it's not B. All right. How do you decide? More conjugation, longer wavelength. So which one has the most conjugation? 3. So this one is which one? The one on the left or the one on the right? One on the right. Right. Increasing means getting bigger. Right? Increasing. All right. So if 3 is the one on the right, then who is the first one? 2. And then 01 is in the middle. So it's either 213 or 312, which was good that you had narrowed it down to that. You need to understand what these dills mean, right? Increasing. Okay? That's all right. Get it squared away before we have one like that on the test. What? Okay. All right. Now we're going to go to. Open this already. Oh. All right, it should be right at the top here. And I'll post the final slides from that. I'll try to get that done today. I should have it. We have a little break in the video there, eh? Okay, chapter 16 is about aromatic compounds. Okay, can you name me one aromatic compound? Good, benzene. Didn't you talk about, didn't you make diphenylbenzene? You talked about benzene reactions, right? So you're going to know everything. Okay, aromatic does not just mean smells good. And if you remember from using benzene in the lab, it doesn't smell particularly good. Did y'all know that that is what was burning their for benzene? Heard about the big fires down by the big fire at a chemical plant last week, and there was a huge thing of benzene that was burning. They had to evacuate. You don't want to breathe benzene. You do not want to drink benzene. You do not want to get benzene on you, okay? But if you get benzene on you, don't panic, wash it off. People who get leukemia from benzene were people who worked like in the auto industry and stuff, and they had their arms and hands in vats of benzene cleaning them. Really great for cleaning oil and grease off stuff. And so that's how come they were using it. But what happened was, because their hands were in the benzene, it was being forced into their body. Okay? And so if you got a little benzene on you, it probably evaporated before. Okay? So no panic. Okay? So, and you probably noticed benzene does not smell very good. Okay? Even though they're called aromatic. Okay? You think a perfume is being aromatic. Well, not benzene. History of benzene. It was isolated in 1825 by Michael Faraday. That's Michael Faraday. He was using whale oil to produce the gas used to light buildings in London. Before they had electricity, they actually used gas. Does that not sound scary? It's scary. He found that there was a liquid residue left over, and they extracted the benzene from it. That's where they got it. Okay. Benzene, y'all probably already know what it looks like. Oh, here we go. In 1834, this guy, Eilhard Mitscherlich, how's that? Determined the molecular formula to be C6H6. It was a long time before they figured out what the structure was. That blew everybody's mind, because it had the same number of carbons and hydrogens, okay? It's not like hexane, which is C6H, what? 14 hydrogens, okay? So he named it benzene, and that's kind of how we ended up with benzene. Okay, aromatic compounds have relatively few hydrogens to the number of carbons. That's called a low hydrogen to carbon ratio. Aliphatic carbons have very high hydrogen to carbon ratio. Aliphatic, that term came about because these are compounds that were soluble in fat. Okay, that's how the aliphatic term came around. They are typically found in oils from trees and plants. Early chemists called them aromatic due to their pleasing fragrance, because some of them smell good, but a whole lot of them don't. Good example of one that we tend to think smells good is cinnamaldehyde. What do you think cinnamaldehyde smells like? Cinnamon. Okay, so there are some aromatic compounds that smell nice, but they don't. Aromatic is different now. Okay, here's a guy named Kekulé. Kekulé is famous for coming up with the two basic structures of benzene that are referred to as the Kekulé. The story goes, and this was written out by him, that he was sitting in front of the fire trying to solve this puzzle of what structure. Okay, like you wouldn't believe if you looked at the history of benzene, they came up with all kinds of wild things trying to figure out the structure. Well, he said that he was dozing in front of the fireplace and he fell asleep and he had a dream. And in the dream were snakes. And one of the snakes bit its own tail and he figured out the structure of benzene. I'm telling you, I don't know. I don't know. So here are the Kekulé forms of benzene, which is, okay, so there's one. Okay. Here is the other one. See the difference? Not a whole lot, is there? Okay. But that would keep them same in energy, right? So you could draw a little resonance and look what you get. Okay, those are called the Kekulé forms of benzene. Whether or not, now there's all this controversy. He didn't really have the snake dream. He came up with that. I don't know. It's still fun to tell. So, okay. So benzene, what do we know about it? We know that it's planar. We know that it's a ring. And there's a cloud of delocalized electrons above and below the plane of the ring. So do you see how we get all this? It looks like two donuts. Okay? It looks like two donuts, one above and one below. Those are the top lobes of the p orbitals and the bottom lobes of the p orbitals. Okay? All of the carbon-carbon bonds have the same length. Okay, they have the same length. I guess I need a different color. Okay, so typically if you are a double bond, you are shorter than a single bond. Right? So if benzene was going from one Kekulé form to the other, it was going from one to the other and back again, the sizes would be different. The single bonds would be around 134 picometers and the double bonds would be around 146. Well, remember what we talked about resonance forms, that they are pictures of how the molecule looks. But what the molecule really is like is all those pictures put together. Okay? The hybrid. Well, what they found is the structure of benzene, the carbon-carbon bonds, every one of them is the same length, and it's 140 picometers. Look where that fits. 134, 146, smack dab in the middle. Okay? In between. Like even exactly in between. Right? Okay. Benzene is unusually stable. Okay? So if you take cyclohexene and you add hydrogen to it and you do that reduction, okay, to make cyclohexane, you get a certain delta H. What's delta H? Enthalpy, heat content. Remember all that stuff? Oh my gosh, I know. It's rough. We expect you to remember everything. Okay, we're not going to calculate. All right? It gives off minus 28.6 kcals per mole. The negative means it's exothermic. Okay. All right. If you took, and they took this, and they multiplied it by 3 for cyclohexatriene, okay? And it should be 85.8. That's 28.6 times 3. 3 double bonds. Well, what they found is they actually got 49.8. it is more stable than they anticipate. Okay, it's more stable than they anticipate. Okay, so for example, here is another way of looking at it. Here is cyclohexatriene, the 85.8, but benzene is already lower in energy before we even get to doing the delta H. Okay, all right, that help you remember that stuff a little? Okay, so what makes a molecule aromatic? It must have I must have missed this one. It must have an uninterrupted cyclic cloud of pi electrons above and below the plane of the ring. Notice this, uninterrupted. All right. Sigh, just don't like me today. Okay. The molecule must be cyclic. So you look at 135 hexatriene, not the cyclic one, just this one, and you'll see that there's a whole lot of pi electrons above and below, but it's not cyclic. Okay, so it cannot be aromatic. Every atom in the ring must have a p orbital. Okay, everyone must have a p orbital. And the molecule needs to be planar. If it's not planar, you're not going to get your donuts. Okay, if it's not planar, you're not going to get your donuts. Now, here's the kicker. The pi cloud must contain an odd number of pairs of electrons. Odd number. Isn't that interesting? How many pi electrons are there in benzene? I will just draw a little picture. Okay, how many pi electrons are there? Each carbon has one, right? Okay, so there's a total of 6. Is that an odd number of pairs of pi electrons? Well, what's 6 divided by 2? There are 3 pairs in benzene. Okay, is that making sense? You can also go 2, 4, 6. 1, 2, 3. Okay, now there's a guy named Huckel. He came out with this lovely little rule, 4n plus 2 equals the number of pi electrons. Okay, so for benzene, you would go 4n plus 2 equals what? How many pi electrons are in benzene? 6. Okay, that's where you get the 6. Now you solve for n. What's n? 4n plus 2 equals 6. N is 1. Higher mathematics today. Okay, n is 1. Is 1 an integer? Yes. So it also solves Huckel's rule. Okay? All right, so here is basically what I just said, okay? So 4n plus 2 equals 6. 4n equals 4. N is 1, okay? It's aromatic. It also has 3 pairs of pi electrons. All right, what about this guy? 4n plus 2 equals 8. Does everybody see how we got 8? That's real important. Okay, so 4n equals 6, n equals 3 halves. Is 3 halves an integer? No. Okay, good. All right, so is this molecule aromatic? No. It has an even number of pi electrons. Okay? 4 pairs of pi electrons. Okay? So we're going to do some more of this, and then we're going to do the nomenclature. Okay? All right, so I'll see you on Friday. Don't forget to talk tomorrow.